Thank you. So this morning I was asked two questions which I would like to answer more precisely before going on. The first question was about why don't we simply compute the integral of L prime over L to obtain the order of the L function at 1? And after discussing with colleagues, but the answer is, I think, quite clear, is that indeed if you take a little circle or a little contour around 1, well, you are going to get an integer, certainly. But this integer is not necessarily exactly equal to the order at 1. There may be a 0 of the L function which is close to 1. And I think it's exactly the same phenomenon that you encounter if you compute the second derivative, for instance, and find that it's 0 to a lot of decimals. This may mean that there is, in fact, a 0 very close to 1. So I think that's really the answer to the question. The second question, I was asked to give a little course on dessin d'enfant. That's a little too long. But I can give you an example, and I thank Cathy for having drawn this beautiful octahedron on the blackboard with the middle plane in the middle. So this is Felix Klein's construction in the case of the octahedron, which is the easiest to draw. If you want to solve the 2, 3, 5, this is to solve the 2, 3, 4 example, the octahedral case. If you want to solve the 2, 3, 5 example, you would have to do exactly the same as I am going to do now, except that you have to do it with an icosahedron, and I'm absolutely incapable of doing this. I'm very bad at drawing. Octahedron I can still manage, but icosahedron is impossible for me. I mean, you can be good at drawing. So what do you do? Well, you take this icosahedron and you take the North Pole. Now you have to consider this as being in the sphere, inscribed in the sphere, which is P1, of course. So you take the North Pole here. If you prefer taking the South Pole, I don't care if you're in Australia. And you do a stereographic projection in the projective sense of all the vertices, I insist, of the octahedron. So the octahedron has 6 vertices, 1, 2, 3, 4, 5, 6. So when you do the stereographic projection, say, on this plane, you get, well, these vertices are already on this plane, so they don't count. Well, I mean, they count, but they're just where they are. This point comes exactly at the origin here. And the North Pole goes at infinity. Okay? So rotating the octahedron in a suitable way, you can assume that on the complex plane, this point is the point, let's see, I. This point is the point minus I. This point is the point 1. This point is the point minus 1. This point is the point 0. And this point is the point infinity. Okay? What's the homogeneous polynomial? We're talking projective here. So we're talking homogeneous polynomial. What's the homogeneous polynomial whose roots, I mean the simplest one, whose roots are exactly these 6 points? It's clear that it's the polynomial f equal, am I writing too small? X times y times x squared minus y squared times x squared plus y squared. Well, x4 if you want xy times x to the 4th minus y4. The 4th root of unity. Everybody agrees? This gives me the 4 points here. This gives me the point x equals 0, and y is the point at infinity, or unless it's the reverse. It depends if you consider y over x or x over y. So this is the basic Klein polynomial associated to the octahedron. You can do exactly the same with all Platonic solids. So in particular with the tetrahedron and with the icosahedron. This polynomial has degree 6. Now, you do a construction which is completely universal. And the reason why this construction works is explained by Klein, but it's better explained, in fact, by Bailey. But anyway, believe me, this universal construction I'm going to describe is exactly the same for all such objects. You first compute a new polynomial, which you call G, for instance, which is called the Hessian of f. So what is the Hessian of f? It's simply the 2 by 2 determinant of second partial derivatives of f with respect to x, twice with respect to x, twice with respect to y, and then with respect to xy, and with respect to yx. Now, of course, since f is a polynomial, the derivative with respect to y and x is the same as x and y. But okay, so this is called the Hessian. Now, you will notice that, in fact, if you do the computation explicitly, if you have a computer algebra system in front of you, you will notice that there is some stupid constant factor here. So you just divide by that constant factor to get the polynomial the simplest as possible. It doesn't matter. You'll see the statement I'm going to give. So this is absolutely universal. Starting from a Klein polynomial, which is a polynomial you obtain from a regular solid, you compute its Hessian. Okay, so what's the degree of this guy? Well, f is of degree 6, so this is of degree 4. This is degree 4, 4, 4. So this is of degree 8, because it's not generic here. We're computing with homogeneous polynomials, so the degrees cannot drop. So this is degree exactly equal to 8. Okay, and the third and final polynomial, I don't know if there is a name for this guy. I call it the Jacobian polynomial. It's the Jacobian polynomial of f and g. Excuse me, there may be a more proper name for this, and maybe people here know what it is. What is this Jacobian polynomial? Well, simply, you take the derivative of f with respect to x, the derivative of f with respect to y, the derivative of g with respect to x, the derivative of g with respect to y, and you take, again, the 2 by 2 determinant, and again, you divide by a stupid constant because you will notice that it's divisible by something. And this thing has degree, well, I don't offer Toblerones, especially for such easy problems. So f had degree 6, so that has degree 5. G had degree 8. This has degree 7, so this has degree 12. So now everybody can guess. F has degree 6, so we raise it to the 4th power. G has degree 8, so we raise it to the 3rd power. H has degree 12, we raise it to the 2nd power. And miracle, this is equal to 0. Completely miraculous. And this works for all Platonic solids. Now, what I've written here is not quite true. But it's essentially true. It's not quite true because it depends on the normalization. I told you, you divide by some factor here, you divide by some factor here. So what is true is that there are constants here, which are rational numbers, really rational numbers. There are constants here and here, which you can put to make this equality true. Still, it's a very powerful statement, since this is an equality about the homogeneous polynomial of degree 24. Okay, that's the magic. Okay, and now you see this is already obtained a first parameterization of the 2, 3, 4 equation. Well, from there on, you work. But I just wanted to explain how this is in fact equivalent to the construction of the Bailey function. But forget this, it's really very elementary. You see?
Sorry for keeping on bothering over. So I've seen this kind of discussion before, but I'm still not sure what it has to do with the Bailey parameter for what.
No, this really would take me too much
Okay,
time.
sorry.
But this you really can do for the icosahedron and get a Klein parameterization of the 2, 3, 5 equation. And then, of course, you have to apply PSL2C. Everything I said before is still true, but at least to get one, this is how you do it. It's really a miracle. I mean, it's absolutely beautiful. Try it on your favorite computer algebra system. No questions? I'll come back to my talk. So can you please turn off the lights, please? Where was I? No. Okay, so I was discussing elliptic curves, and I told you roughly of 4 methods. So 2 descent, 3 descent, well, higher descents if you want. Use of L functions just to compute the rank, and the Heegner-Point method. So let's study these methods in turn. Let's start with the easiest method, which is 2 descent, which is very, very classical. In fact, there is an excellent book of undergraduate text of Silverman Tate, which explains this in the utmost detail and very, very well written. So for those of you who don't know 2 descent, start with that book. It's really marvelous. I'm not talking of Silverman's book. I'm talking of Silverman Tate, which is an undergraduate text. So when there is a 2 torsion point, 2 descent, in fact, is much easier from an algorithmic point of view. But to explain, it's in fact harder. So I prefer, in fact, immediately starting with the 2 descent in the general case when you don't have a 2 torsion points. What does this mean? This means that if you write your equation y squared equal x cubed plus ax plus b, as on the bottom of the slide, then this polynomial x cubed plus ax plus b is irreducible over q. Doesn't have any irrational root. Okay, so the general idea of descent, initiated by Fermat, is, as I said already, to map a large point on a given curve to much smaller points on other curves. And as I mentioned, smaller means really smaller. The number of digits is divided by something. It's really remarkable. Okay, so we are going to study 2 descent in the case where there is no torsion point, no 2 torsion point. So you take an equation y squared equal x cubed plus ax plus b. You can always assume a and b integers. And we will call theta a root of this equation and consider the cubic number field k equal q of theta. Now remember, we are in a day and age where computing on number fields of reasonably small degree and discriminant is something completely trivial. So I know absolutely everything I want about q of theta. So the key observation, which is very, very old, is that you can define a map, which is called the 2 descent map, alpha, from the rational points of E. I insist, it's from the rational points, not from any point, to the quotient, the multiplicative group, which is the quotient of non-zero elements of K, the multiplicative group of K, by squares. And how do you define this map? It's really very simple. You send the origin of the elliptic curve, the point at infinity, to 1. Well, because as I will state in a minute, it's a group homomorphism, so you have to do that. And the map on affine points is simply sending a point with coordinates, with affine coordinates xy, simply to x minus theta. So you just take the x coordinate, subtract theta from it, and that gives an element in k star, and you take its class modulo k star square. It's really extremely simple. Now, well, okay. And the fundamental result, which is just a verification, I mean, you just write the equations, and this is done in Silverman Tate. In fact, I think it's, their book is beautiful, but if you look at the proof of these facts, I mean, it's really so detailed that after some time you really get tired, because, I mean, they really do absolutely everything that you need to do. But sometimes it's an exaggeration to do all the details. In their case, really, absolutely nothing is omitted. So the fundamental fact, I tried to use a consistent color coding, but there is a misprint here. Alpha should be in blue. But anyway, alpha is a group homomorphism. That's the first fact, which is easy to check. But the problem, I mean, why does it take so long to check? It's because there are so many special cases. I mean, you have to consider whether points are equal, opposite, so on. I mean, if any one of you has written already explicitly as an exercise the group law on an elliptic curve, you will know that it's extremely painful because you have, I don't know how many special cases to consider. And it's the same thing here. You have, I don't know how many special cases to consider to prove that it's a group homomorphism. Of course, if you just look at the generic situation, then of course it's trivial. But okay, anyway, it is a group homomorphism. And second very important fact, you know exactly what its kernel is. It's exactly 2e of q. Let me explain this notation. 2e of q, the group law on the elliptic curve is always denoted additively. It's not denoted multiplicatively. So 2e of q is in fact the set of points p plus p, where p is a rational point. P plus p equals 2p. But of course, you can think of it multiplicatively and say that it's the set of squares of points on the elliptic curve if you want to think of the elliptic curve multiplicatively. But usually one thinks of it additively. So, in particular, since we know the kernel, it induces an injective group homomorphism from e of q divided by 2e of q to k star divided by k star squared. And the rank of the elliptic curve is exactly equal to the F2 dimension of the image of this map. The reason for this is we have assumed that there is no two torsion. So the rank cannot be, the dimension over F2 of the image of alpha cannot be increased by two torsion. So you see, it's really amazingly easy. The only problem now is to compute the image of alpha. But alpha is completely explicit. Still, it's not that easy. Otherwise, everything would. So we need to describe the image of alpha. For this, I introduce a notion. So if you allow me, the name which I coined here, I coined it myself. Probably nobody else in the world uses it. I don't care. I think it's much more appropriate than the name which is usually used. I defined the T-Selmer group of a number field, warning for those of you who know what the Selmer group of an elliptic curve is. In fact, I will give it in a subsequent slide. Here I'm defining the Selmer group of a number field. So the T-Selmer group of a number field is defined in the following way. T is a finite set of prime ideals. By the way, why do I call it T? Well, for an evident reason. Usually a finite set of prime ideals is denoted by S, but here I'm not going to have S sub S. I mean, okay. So T is a finite set of prime ideals of my number field. U sub T of K is the group of T units. So a T unit, it simply means that the valuation of the unit of the element U is equal to 0 when P is outside of your finite set T. So if T is empty, of course, it's an ordinary unit. CL sub T of K is the T class group. What is the T class group? Well, maybe it's not exactly the definition, but you can take this as a definition. It's the ordinary class group divided by the group generated by the classes of elements of T, by the prime ideals in T. Okay, and now come the new definitions. Those are very classical. What I call a T virtual square, U, is simply, well, it's like a T unit, except that instead of asking that the valuation is 0, we ask that the valuation is even for all P not belonging to T. By the way, there is a misprint in the second line. It should be a Gothic P not belonging to T and not little p belonging to T, not belonging to T. It should be the same as the, well, I don't have anything to point, but you can see, I mean, the P's have to be the same script, same font. So a virtual square is something for which the valuation has to be even everywhere, except perhaps on T. And the T-Selmer group, but of course, even if T is empty, this is not a completely trivial thing. I mean, you ask in that case, if T is empty, that the valuation over prime ideals of U has to be even for all prime ideals, but that doesn't mean it's a square. And the T-Selmer group, S sub T of K, is exactly the obstruction to that. It's the quotient of the unit of the group of T virtual squares by the squares, because of course the squares satisfy this. Okay, this is a name and a notation which I introduced. You may not like it, but I think that it's really better than what's used usually. The usual notation for this group is K parenthesis S T comma 2. Take the one you like. So S sub T of K, the Selmer group, is something which is very well understood and which you can compute in microseconds on any reasonable computer algebra system, if of course your field is not too huge. And in fact, it's isomorphic to the product, direct product, it's a split exact sequence of the quotient of T units by squares by the part of the T class group which is killed by 2. So that's the first line above. St of k is isomorphic to ut of k divided by ut of k squared cross CLT of k bracket 2. This means the part killed by 2. Ideal classes whose square is trivial. So it's very easy to compute. And the basic result, which links the image of alpha, which is what we want to compute, which is very easy to prove once again, it's just some easy computations to be done, is the following. T, until now, T was completely arbitrary. I gave you arbitrary definitions for an arbitrary finite set of primes. Here we're going to specify the primes. In fact, we want to take T as small as possible. So here are the prime ideals we take. I call them Q here instead of calling them P for a good reason. But so T is the set of prime ideals Q which have two properties. First, which are very linked, but okay. Q has to divide the algebraic integer 3 theta squared plus a. Remember, our equation is y squared equal x cubed plus ax plus b. So when you take the derivative of this, it gives you 3x squared plus a. And when you replace x by theta, it gives you 3 theta squared plus a. So this is in fact equal to f prime of theta, if the equation of the curve is y squared equal f of x. Okay, that's the first condition. The second condition is that little q, now this is not a misprint, this is the prime number which is below q, must divide the index of z of theta in the full ring of the z integers. In particular, if the full ring of integers of k is equal to z of theta, then the condition is that q doesn't exist. I mean, so t in that case is empty. Okay? Then the image of alpha is equal to the group of classes of U. I put a bar above U just to mean that it's classes modulo squares. Remember, the Selmer group is the class of elements satisfying such a property, modulo squares. So it's a group of classes of U such that the norm of U, well, the norm, you know what the norm is for any lift, that doesn't matter, is a square in the rational numbers, and such that there exists a lift. Now, you have to look at the difference between the two things. The first statement that I ask is that the norm is a square. But you can lift U in any way, since the difference between two lifts is a square. Well, if one lift, its norm is a square, any lift will have its norm to be a square. So this is really a condition which you can take any lift to check. On the other hand, the second condition is much nastier. That's why I put it in red. The second condition is that there exists a lift U which is of the form x minus theta. And I immediately tell you, well, in fact, that's the last line of the slide. It's this last condition which makes the two-descent method not work in many cases. Okay, so comments. Sometimes the index, as I said, is 1. In fact, it doesn't happen so often, but it may happen. In that case, T is empty. But of course, the Selmer groups may still be non-trivial in that case. And the second comment, which is what I just did, the condition on the norm is completely algorithmic, but the existence of a lift is not algorithmic. And luckily, it's feasible in many cases, but still, I'm, of course, going to expand on this in the next slides. I would like to note, to attribute this result, because it's not in the literature, this result that Q divides the index zk over z of theta, we have not been able to find this in the literature, although the proof takes only a few lines, and it was observed in his habilitation by Denis Simon. So I would like to mention his name at this point, because it's really a nice observation. Because to do the computations, you really want T to be minimal. There are some extra conditions that you can ask, that you can add. For instance, you can show that the Tamagawa number associated to Q has to be even, for instance. Conditions like this. But of course, you may not know what the Tamagawa number is, but it doesn't matter. You want to add as many conditions as possible on T to make T as small as possible. Okay, so how does this work? Well, we consider the group G of classes U and ST of K, whose lifts have square norm. This is completely algorithmic to determine. No problem. Just use your favorite computer algebra system. It tells you this in microseconds. But now what it doesn't tell you is if U bar has a lift x minus theta. So how do we do this? Well, we lift it in any way. We write U as U2 theta squared plus U1 theta plus U0, any lift where the UIs are integers. And all other lifts, by definition, since we have made the quotient by squares, any lift is of the form U times gamma squared, where gamma I can write as C2 theta squared plus C1 theta plus C0, where the CIs are integers. Well, in fact, I'm cheating. I'm saying they're integers. It depends exactly if the ring of integers is not equal to Z theta. They may have little rational denominators, but let's forget this. It doesn't change in any way what I'm saying. So you write U gamma squared, and you want U gamma squared to be of the form x minus theta. So what is known? What is unknown? What is known is the UIs, okay? U2, U1, U0. What is unknown is C2, C1, C0. So when you expand the product as in powers of theta, you get U gamma squared equal, well, something times theta squared plus something times theta plus a constant. And the somethings, if you can just look, I mean, it's clear. Gamma squared is quadratic, is homogeneous and quadratic in the CIs. So the coefficients of theta squared, theta and 1, are quadratic forms in C0, C1, and C2, clearly, which I write Q2 minus Q1 and Q0. So they're completely explicit quadratic forms, depending on the UI. And the first condition that this U gamma squared is x minus theta is that there is no coefficient of theta squared. So the first essential condition is that Q2 is equal to 0. The second condition is that the coefficient of theta is equal to minus 1. That's why I put a minus sign. So that means that Q1 has to be equal to 1. And there is no third condition, because the third condition is that Q0 is equal to x, but that's not a condition. It means that you set x equal Q0. So what you have to solve is the intersection of two quadratics. Q0 equal 1, Q2 equals 0, and Q1 equal 1. That's the intersection of two quadratics. But the problem is, when I defined elliptic curves as the intersection of two quadratics, I may have forgotten to tell you that, of course, you take the intersection of two quadratics, but of course you assume, as usual, that you know a rational point on this intersection. Here we don't know anything. So it's difficult. So what do? Well, we start from the first equation, Q2 equals 0. Now, that's very nice, because that's a quadratic form equal to 0, no problem. We have a beautiful theorem called the Hasse-Minkowski theorem, which is one of the very rare local to global principles which exist. And that tells you that if a quadratic form is equal to is solvable globally, if and only if it is locally solvable everywhere. So that's very nice. By the way, do not make the mistake of thinking that the Hasse-Minkowski is true for non-homogeneous quadratic forms. I mean, if you take something which has a quadratic term and a linear term and a constant term, maybe, for instance, this may be locally solvable everywhere, but it's not globally solvable. So warning, this is not always true. But here it's homogeneous, so there's no problem. And so you just check if it's locally solvable. If it's not locally solvable, you just throw away this U. This U cannot be lifted, no problem. Okay. Now, if it is locally solvable, it is globally solvable. And then there's a second fact, which is really nice, which is that when you have a three-variable quadratic equation, you can parameterize it explicitly when you know, of course, the solution. You can give an explicit parameterization exactly of the form that I mentioned this morning for the super-Fermat equations. That is, it's homogeneous polynomials, in this case of degree 2, again, homogeneous in two variables. Exactly the same as this morning. So you can parameterize. Good. So now we parameterize. So we know that C0 is equal to something in S and T, quadratic. C1, same thing. C2, same thing. And we replace in the second equation, Q1 equals 1. And then we clear denominators because we want now to work in integers. And, well, no, it's not that, excuse me. The parameterization involves a constant of homogeneity, of course. So you don't have only S and T, you have, in fact, D also. Anyway, once you do the replacement, it's clear that in Q1, once you have replaced, you get a quartic. And instead of writing that the quartic is equal to 1, in fact, the quartic is equal to a square because of the homogeneity condition. So what you have to solve is a hyperelliptic quartic equation, y squared equal q of x, where q is completely explicit. And this is where we stop because, well, we don't know how to solve this. It would be an elliptic curve if we knew a point on it, but that's exactly the whole problem. We don't know a point. However, we still can do a little more. We can first test if this thing is locally solvable. Ah, good. So we test if it's everywhere locally solvable. If it's not everywhere locally solvable, we're very happy. We can throw away the u. But if it is everywhere locally solvable, then we're a little stuck. So what can we do? Well, two things. We can launch a computer search to see if there are solutions of y squared equal q of x. Just launch. And maybe, of course, use some intelligent methods of looking for solutions, but hope for the best. And if you don't find that, well, the other method you can do is to use what is called second descent. I will mention this. Okay, but let's come back to the slide itself. So the group of U such that the corresponding quartic is everywhere locally solvable, which is still something you can check out algorithmically, is called the two-Selmer group of the elliptic curve now. Warning, this is another object. It's called S sub 2 of E. It's not S sub T of K. Okay, it's the two-Selmer group of the elliptic curve. And it's the smallest group. Of course, you want to have the group as small as possible, not as large. The smallest group, which contains E divided by 2E, which is, of course, what you want to compute. It's the smallest group, which is algorithmically computable using two descent. Of course, using three descent, you may find some other group, but using two descent, that's the best you can do. And in fact, the quotient of S2 of E by the unknown part, by E of Q over 2E of Q, is exactly the obstruction to the descent. And by definition, is the Tate-Chafarich group of E killed by 2. So this you can take as a definition of SHA of E of 2, of course, but I would need to define what the Tate-Chafarich group in its entirety is, but you can easily deduce the global definition just from this part about 2 descent. So that's the obstruction. So if the Tate-Chafarich group, the 2 part of the Tate-Chafarich group, is trivial, 2 descent works. If it's not trivial, well, then you try 3 descent. So anyway, 2 descent is quite powerful. By the way, why did I call my Selmer group of a number field a Selmer group? It's because it's really absolutely copied on the elliptic curve case. You don't need to put the lights. The fundamental exact sequence is 0 gives E of Q divided by 2E of Q, goes into the Selmer group, goes into the SHA of E killed by 2, goes to 0. That's the fundamental exact sequence, which we have here. And in the case of the Selmer group with a number field, you have 0 gives U sub T, well, let's forget T, U of E divided, U of, excuse me, of K divided by U of K squared, goes to the Selmer group of the number field. I don't put any index, but I take T equal empty set. And here you have the class group of K killed by 2. And it's well known to the experts that, you see, this analogy is much stronger than it looks. I mean, the rational points on the elliptic curve correspond to units of a number field, and the Tate-Chafarich group corresponds to the class group. And so you see the Selmer groups correspond. That's why, well, I'm not, at my age, I'm not going to ask that the whole world takes my own notation, but that's why I consider that, why denote this guy as K of t and 2 instead of denoting it naturally s of k. Anyway. So as I mentioned, if two descent is quite powerful, it works in quite a number of cases, and it's the basis of Cremona's MW rank program, which is the program I think that everybody uses in the world to compute ranks and generators of the Mordell-Levé group over Q. And if it fails, well, apart from 3 descent, to which I'm going to come, you can try second descent. And second descent essentially means, well, you start from the quartics and try to solve them using analogous method. And as an exercise, which you cannot do in 5 minutes, but do it when you have time, try your 2 descent skills for these two equations. Y squared equal x cubed plus or minus 16. It's one of the easiest examples, and it's in particular very easy because the answer is that they have rank 0. But still, you have to prove it. So that's 2 descent. You see, it's really not very difficult. 3 descent. So 3 descent is not very difficult either, but would be a little long to explain. So I'm going to specialize to an application which I find very nice. The goal of my application is the following. I'm given non-zero integers a, b, and c. I would like to determine whether ax cubed plus by cubed plus cz cubed equals 0 has a non-trivial solution. Non-trivial meaning, of course, all 3 non-zero. If you want, if there is a point, if there is a rational point on the corresponding projective curve. This is not so easy. I mean, of course, you can look at local solubility conditions, as usual. But once you look at local solubility, as usual, well, when you have cubics, the local to global principle doesn't work. You can try and factor in number fields, and indeed you can. In fact, it's not very difficult to see that you can do a very simple transformations on x, y, and z, and you can assume that a is equal to 1, if you want. That's no problem. And you can do some sort of algebraic manipulations and get some conditions, some algebraic number theory conditions involving class groups again and so on. And okay, you can solve some cases like this, but it's really not at all systematic. Again, you have class number conditions. What I'm going to show you is how, using 3 descent, you can do it really systematically. Well, modulo, as usual, the fact that you can compute the Mordell-Levé group of a certain elliptic curve. But okay, well. Okay, so for this, I consider the following elliptic curve, which is really the nicest elliptic curve you can think of to apply 3 descent. You can't do better, which is y squared equal x cubed plus n squared. So this is really extremely nice. You can see immediately there is a torsion point of order 3. You take x equals 0 and y equal n. Well, maybe you don't see the operation in your head, but it's really completely trivial to see that t is torsion of order 3. And I'm going to do exactly the same as I did for 2 descent. I'm going to define a 3 descent map, alpha, which in that case is really extremely simple, from the rational points of my elliptic curve to the quotient of q star over q star cubed. Here I don't have any number field because I took such an easy equation, but of course, if I take a more complicated elliptic curve, even when there is irrational 3 torsion, I would have to have a larger number field here, but here I'm in Q, it's even simpler. So I have to send the origin of the elliptic curve to 1. Forget the second statement for a minute. And I do exactly the same as for 2 descent in the sense, but the formula is slightly different. Alpha of x comma y is not x minus theta, here it's y minus n. Well, that's how it is. So it's the y coordinate minus the number n. Now you see, there is a slight problem here. Of course, this is modulo q's. I'm in the group q star divided by q star q. There is a slight problem when y is equal to n, because of course 0 doesn't exist in q star. So that's why when y is equal to n, this occurs exactly for x equals 0. So this is exactly the point t. This is why I need to give the value of alpha of t also. And the value of alpha of t, if you think about it, is completely determined. Okay, I gave on the slide the value is 4n squared. But in fact, I didn't need to tell you what it was. Because in fact, it's automatic. Let's do the computation. Very simple. See, t is of order 2. So what's the opposite of t? It's of order 3, excuse me. So what's the opposite of t? The opposite of t is 0 minus n. But that's also 2t, since t is of order 3. 2t is equal to minus t. So 0 minus n. Okay, good. What's alpha of minus t then? Alpha of minus t, or 2t, is equal to minus n minus n. So it's minus 2n. And how do I get alpha of t? Well, simply by noting that t is equal to 4t. And 4t is twice 2t. So since I want alpha to be a group homomorphism, I'm going to have minus 2n squared. And that's 4n squared. So I have to have alpha of t equal 4n squared. I hope my proof wasn't too hard to follow. Anyway, you easily check, exactly like in the two descent case, that alpha is a group homomorphism. And the kernel is easy to compute, but I don't want to give it to you. It's not 3e of q. It's something much... okay, because it's exactly like in the case where you have two torsion. I didn't describe the kernel in the case where you have two torsion, because for this I would have had to introduce the isogenous elliptic curve. In this case, it's the same. So, but forget it. We don't need it here. So now let's go about our business. We have our descent map. So let's consider the projective curve on which we want to find points. C equals C sub ABC with projective equation ax cubed plus by cubed plus cz cubed. And I claim that this projective curve is intimately linked to the curve E equals, corresponding to n equal 4abc. E equals E sub 4abc. So E is the curve y squared equal x cubed plus 4abc quantity squared. So what's the link? Well, here's the proposition. You just check. I just define a map, phi. So phi of x, y, z is equal to minus, well, you can read, minus 4abc x, y, z, minus 4abc dy cubed minus cz cubed, and ax cubed. I could divide, of course, these three quantities by a, since it's homogeneous, but it's better to write it like this because it's more symmetrical. So the statements, which again are completely immediate to prove, I mean, you just check, is that phi sends the group that we're looking for, which may be empty, C of Q, inside E of Q. So it sends C. In fact, excuse me, this statement is dumb. The map sends C of anything into E of anything. It has nothing to do with Q. Excuse me. I mean, it just sends C to E as projective curves. In particular, of course, it sends C of Q into E of Q because the coefficients are rational. But okay, the second statement is that if you take a point, you take the set of G, the set G of points x, y, z, and E of Q in projective coordinates, such that there exists a lambda, a non-zero lambda in Q, with C times, well, look at the condition, y minus 4abcz equals bz lambda cubed. So there exists a lambda such that this. Then the image of the map phi, which is really what I need, is exactly equal to the group G, together with the origin of the elliptic curve in case where the quotient C over B is a cube, a rational cube, and in addition the torsion point T if B over A is a cube. In addition, if you want, it's immediate to write down the pre-images of these points when they are indeed in the image. I don't need that. And the third statement, which is really what I want, which is a consequence, in fact, of what precedes, is that the set C of Q is non-empty, which is really what I need, if and only if the quotient B over C modulo Q, so if you don't want B over C, you can write B times C squared. It's the same thing, modulo cubes. So if and only if B over C modulo cubes belongs to the image of the three descent map alpha as a subgroup of Q star over Q star Q. So I'm going to speak about this, of course, now, but you see, it solves entirely the problem as soon as, of course, you can give the image of alpha. And giving the image of alpha is essentially equivalent to computing the Mordell-Weil group of the elliptic curve E sub 4 ABC. So the proof is very simple, but I would like to go over one small point of it. 1 and 2 are you just simply check. I mean, you write the equations and it just works. I'd like to explain 3 just in a second. Of course, C of Q is non-empty if and only if the image of C of Q is non-empty. And this is true if and only if, that can, because of statement 2, it's true if and only if there exists x, y, z in E of Q and lambda such that, the same thing as in 2, or if C over B or B over A are cubes. That's just statement 2. And what I would like to mention is that this lambda, in that case, is explicitly given in terms of the solution in C of Q. Lambda is equal to 2c little z divided by little x. Warning, I'm using a consistent notation, hopefully here. Little x, little y, little z are elements, are projective coordinates on my curve C, while capital X, capital Y, capital Z are projective coordinates on my elliptic curve E. So lambda is given by this formula, 2cz over x. And this is easily seen to imply that the quotient B over C belongs to the image of alpha. So really the proof is. By the way, I would like to thank, what's his name? No, I know the last name. It's the first name I'm trying to remember. Last name is Fisher. First name is Tom Fisher, for explaining this to me. So to test local solubility, let's see, I have 3 minutes. To test solubility of this equation, we proceed as follows. First, we test, of course, for local solubility. That's very easy. Then we compute the Mordell-Weil group of E of Q, E sub 4ABC of Q, using, for instance, 2descent or the software package, or in fact 3descent, which would be more intelligent here. Anyway, we need to compute the Mordell-Weil group. We hope that we obtain it. And of course, if we don't obtain it, then we're stuck. So let's call P sub I from 1 to R the basis of the free part given by the program. And the non-free part, well, we always have, of course, a torsion point of order 3 on our curve P. And we know that the F3 dimension of the torsion part is always 1. It's not 2. There cannot be a Z over 3 times Z over 3. That's impossible. So the points, if I set P0 equal T, then the PIs from 0 to R form an F3 basis of E of Q divided by 3 of Q. So that's of dimension R plus 1, because here there is free torsion. And then we simply check by linear algebra over F3, that's really much simpler algebra than what Dan is asking us to do, that B over C modulo cubes belongs to the group generated by the images by alpha of PI. Don't forget that alpha is completely explicit in Q star over Q star cubed. So this is simply linear algebra. It's completely algorithmic, of course, apart from the Mordell-Weil computations. So if the chairman will allow me, I would like to give 2 examples of this, and I will stop. Is this okay? So the first example, well, historically, the most famous example is due to Selmer. It's with coefficients 3, 4, and 5. But on purpose, I'm going to do some more difficult examples, because that one can really be treated very easily using that method. So why am I giving such a crazy example? I'm trying 1, 55, and 66. Well, there is a good reason. It's because before Tom Fisher explained to me this method, I only knew of the number field method. And I was able to give the complete solution to these equations up to maximum of A, B, and C equals 65. And that was the first equation I didn't know how to solve. Okay, but in fact, it's very easy using this. So it's everywhere locally soluble. As far as I know, I cannot solve it algebraically. So we use the above method. So what do we find? Well, the torsion subgroup is very easy. It's a torsion subgroup of order 3 generated by the torsion point, which is 14,520, which is probably 4 times 55 times 66, something like that. Immediately, you use MW rank, and there is MW rank. I don't know how he does it, but it's absolutely instantaneous. Gives you that it's a curve of rank 1, that it has a generator which has, in fact, integral coordinates, 504 and 18,000 something. You compute modulo cubes the image by alpha. Remember that alpha is completely explicit. There is no difficulty. So alpha of P0, the torsion point, is 2 squared, 3 squared, 5 squared, 11. Alpha of P1 is 2 times 3 squared. And you compute that modulo cubes, B over C, is 2 squared, 3 squared, 5. Well, if you think about it, you're stuck. You cannot, I mean, if you use P0, you're going always to have 11s, unless, of course, you take P0 cubed. But then, since we're working modulo cubes, it doesn't work. So you're going to always to have 11s. So if you don't want to have 11s, and this is the case, you have to use only P1. But if you use only P1, you're never going to have a 5. So the linear algebra you can do in your head. You don't need to go to a computer for that. So B over C is not in the group generated by alpha P0 and alpha P1. So there is no solution. Immediate. Of course, the non-trivial part here, of course, is MW rank. But in fact, it took a tenth of a second. Now, descent is not always negative. It can give you positive results. So let's take this other equation. X cubed plus 17y cubed plus 41z cubed. Now, during my experimentation before I met Tom Fisher, I had solved this, but how did I solve it? Well, I put my computer, and after running quite some time, it gave me an explicit solution. I was very happy. But in fact, it was stupid, because I could have found the solution much faster by using this. And this is how you do it. Torsion subgroup, you know. Rank 1, well, MW rank tells you immediately what it is. I don't know how he does it, but the generator is pretty large, but it's instantaneous. Okay, who cares? Maybe it uses the Heitner-Point method, but I don't think so, because in fact Heitner is not programmed in MW rank for the moment. So the generator, you see, has a pretty large height, pretty large denominators. But on the other hand, if you compute modulo cubes, well, you have alpha P0, alpha P1, B over C, and so on. And you can see that this time, B over C is in the image of alpha. In fact, it's alpha P0 plus P1, simply. So now you simply compute P0 plus P1. It's a big point in projective coordinates. Here it is. You compute the lambda. I remind you that there is a lambda such that, and so on. You find that lambda is this rational number here. And I remind you that lambda is 2z over x. So you find z over x. And of course, everything is projective. So at the end, you find z equal that, x equal that, y equal that. And as you see, looking for this on a computer is slightly painful. While here, it's completely instantaneous. Thank you.